Aloha everyone, my name is Corinne and I'm presenting a work done with my colleagues from the University of Toulouse and the CNES. This work is about the estimation of the sea level anomaly slope. Satellite radar altimetry provides data that can be useful for ocean monitoring, such as sea level anomaly signals, which I will call SLA in the following. The spectrum of this data is widely used to analyze different quantities, such as the energy cascades between large-scale, mesoscale, and submesoscale dynamics. This spectrum, or more exactly the power spectral density, or PSD, is usually estimated through a cumulated weighted periodogram. And then the slope, which is a parameter of interest, is estimated by some linear regression on the PSD in a log-log scale. This raises two questions. First, using a cumulated periodogram means averaging several spectra, which is good for reducing the variance of the PSD, but the corresponding SLA segments can be related to Earth footprints distant from hundreds of kilometers. How can we guarantee that SLA is stationary? I mean that the different SLA segments whose PSD are averaged have the same slope. Second question comes from the use of the periodogram itself. The periodogram means using a weighting window, such as 2K window, rectangular window, or anything like this. And it is well known that this window is responsible for a convolutive bias in the PSD estimate, and therefore a bias on the slope estimate. How can we overcome these two problems? This was the objective of our work, to propose a new PSD estimation well suited for signals with a spectral band of interest in a very, very low frequency range, as it is the case for SLA signals, using short signal segments, namely one segment of 3,000 of samples, which will be good for stationarity, and avoiding the problem of window choice. Our proposed solution is called R-warp. It consists of 3 steps: frequency warping, spectral analysis, and slope estimation. The main idea is the spectral analysis, which is not FFT based, but rather based on autoregressive modeling, AR. This AR spectral analysis is well known as an alternative to FFT-based methods for short signal segments. No window effect, small variance, as you will see in the next slide. More details are given in the paper. Here are some results on real signals. More validation, more results on the paper. Here, the SLA are coming from the equator area, which is known to have low values of the slope, and more important, mostly stationary. I mean, the different SLA segments should have almost the same value of the slope. On the left here, you see the results of 52 slope estimations made on 52 SLA segments of 3,000 samples each. In blue, the results of the periodogram, which obviously cannot be acceptable because it gives very different values of the slope, going up to 4, 5, even negative values, while in red you have the R-warp results, which seem more reliable because they give a quite constant value, which was expected in this equator area. And the mean value is 1.45, which is in agreement with the slope estimated by the conventional method on the whole 52 segments. And on the right, you see an example of a PSD estimated on one segment of 3,000 of samples. In blue, the periodogram with a huge variance, and in red, the R-warp result, the R-warp PSD estimation, which is smoother, and then you can understand that the slope will be easier to estimate. As a conclusion, we have presented a new method to estimate the slope of SLA signals. In the paper, you will find more details about the method, more validation on simulated SLA signals, and more results on real data. What is important that we have shown that this R-warp makes possible PSD and slope estimation on short SLA segments. Please feel free to download the corresponding MATLAB code and to test it. Thank you for your attention, and aloha.